Welcome to another video lecture. In the last lecture, we discussed about signal flow graph and how can we determine transfer function by using signal flow graph. So we started with the basic definitions and terminologies used in signal flow graph, like what is path, gain, loop, non-touching loops, etc. And we also discussed about the Mason's gain formula by which we can determine the transfer function. The formula is P1 delta 1 plus P2 delta 2 up to Pk delta k divided by delta, where we define these terms Pk, which is the path gain of the kth forward path. We defined delta k. Now let's take one example to understand this signal flow graph method to determine the transfer function and how to calculate these parameters P1, P2, P3, delta 1, delta 2, delta 3, and delta n. So let's take one example. So here we have a block diagram. The question is, first we need to convert this block diagram into a signal flow graph, and then by using Mason's gain formula, we need to calculate the transfer function of this block diagram. So the purpose of this question is to determine C by R, which is the transfer function, by using signal flow graph. So the first step to convert a block diagram into a signal flow graph is to find out the nodes. And in the previous class, we discussed that the variables, system variables, act as nodes. Here, the input is a system variable, the output is system variable, the summing elements here, these are the system variables, and the takeoff points are also the system variables. So let us first denote these nodes by some name. R is already input node. Let us assume this summing element to be a node A, this summing element node B, this summing element node C, this takeoff point node D, this takeoff point node E, and this already output node C. So there are 1, 2, 3, 4, 5, 6, 7 nodes are there. So how to convert this block diagram into a signal flow graph? We will have, first of all, we have input node R. We will have output node C, and in between we will have different nodes like node A, node B, node C, node D, node E. Now from input node R towards node A, we have gain value equals to 1. There is no gain in between input node R and A. Between node A and B also we don't have any gain, so there will be unity. Gain between node B and C, we have gain G1. So between B and C, we have gain G1. Between C and D, we have gain value G2. Between D and E, again, we have a gain value G3. And between E and C, we have again unity. So it will be 1. Okay. So between node terminal D to node terminal B, we have a feedback H, and it is connected with a summing element with a positive sign. So we will have from D to node B, we have a feedback, and this value is H1. Similarly, we have from node to E, node C, we have feedback H2. From node E, node C, we have feedback H2, and it is connected with the negative sign. So we will put a minus H2 there. And from node E to node A, we have a feedback node E, node A, we have a feedback. The value equals to, since there is a negative sign there and there is no gain is given as such, so we put gain equals to minus 1, because it is the summing element, there is a negative sign there, so we will put a minus 1 there. So this is how we will convert a block diagram into a signal flow graph. Okay, so in the next stage, we will calculate the transfer function using the signal flow graph. We already discussed in the previous class that the formula for transfer function calculation is this one. We already discussed this in the previous class, which is P1 delta 1 plus P2 delta 2 up to Pk delta k. But P1, P2, P3 are the path gain. So in this particular question, how many forward path we have? So forward path, as already discussed in the previous class, is the path which goes from the input node and to the output node, which starts from the input node and which terminates at the output. So how many forward path we have in this signal flow graph? As you can see that we have only one forward path which goes from in this direction. So the path gain, so we have only one forward path. The path gain of this forward path P1 will be, all the gains of this forward path will be multiplied. So 1 multiplied by 1, multiplied by G1, multiplied by G2, multiplied by G3, multiplied by 1. So the overall gain, path gain of this forward path P1 will be G1 multiplied by G2 multiplied by G3. So only one forward path we have. So the formula for this transfer function will be reduced. It will be only T1 delta 1 divided by delta. Now we need to calculate the value of delta, and the value of delta, this is the value of delta, which is 1 minus sum of loop gain of all individual loops. So first of all, we need to calculate the loop gain of all individual loops. So how many individual loops we have? Now the definition of loop is which starts and which originates and terminates at the same point. So if we take this starting point and this goes like this and terminates at the same point. So this is one loop. Again, this is also a loop which starts and terminates at this position. Let me highlight this. So this is also a loop here, and this also a loop here, and this also a loop. It starts and terminates in this position. So basically there are three loops. Let us define these with L1, L2 and L3. So let us define first loop 1, L1. The value of L1 is the gain of all the value of all the gains in that particular loop, which is suppose I am considering this loop here. So the value of all the gains is G2, G3 and H2. So it will be minus G4, G3 and H2. Similarly, for second loop, which starts from node B and terminates at B also. So this, all the loops are G1, G2, H1. And the loop 3, which starts from node A and terminates at node A, all the gains are G1, G2, G3. There is a minus 1 also. So this will be minus G1, G2, G3. So these are the three loops we have. Now, the second point here in the delta is the sum of loop gain product of two non-touching loops. The non-touching loops are the loops which do not have common nodes. But if we will see in all these three loops, L1, L2 and L3, we have common nodes. Like if we talk about L1 and L2, this is L1, this is L2, this node C is the common node. Similarly, from L2 and L3, this is L2, which starts from D, and L3, which starts from node A. We have several common nodes like node B, C, and D also. And similarly, from L1 and L3, we have several common nodes. So if we talk about non-touching loops, we denote non-touching loops with anti. There is no non-touching loop, so the gain product of non-touching loop is C. Similarly, there are also no three non-touching loops, and the value of delta 1 is the value of delta obtained by removing all the loop touching the kth path. So delta, first of all, let's calculate delta, which is 1 minus sum of all individual loops, which is L1 plus L2 plus L3, plus sum of gain product of non-touching loop, which is 0. So this will be 1 minus L1 minus L2 minus L3. Now, if the value of delta 1 is the value of delta, which is 1 minus all the loops removed from kth forward path. So we are talking about forward path P1. We talk about forward path P1. These all loops are connected, or you can say are touching the forward path P1. So if we will remove all these loops, the value will comes out to be 0. So the value of delta 1 is 1. So finally, the transfer function, if we will put all the values in this formula, P1 delta 1 upon delta, the transfer function value comes out to be P1 is G1, G2, G3. Delta is 1 divided by delta, which is 1 minus L1. L1 is plus G2, G3, H2, minus L2 is G1, G2, H1, minus L3 is G1, G2, G3. So this is the overall transfer function which is given by the Mason's gain formula. Let us take one more example to understand the signal flow graph. In this example, we have nodes represented by numerical values 1, 2, 3, 4, and 5, in which 1 and 5 are the input and output nodes. And the gain values are represented by the alphabets. Like in between node 1 and 2, we have gain A, and this branch is having node which is having gain B, and between node 2 and 3 we have gain D, and so on. So for this signal flow graph, we need to calculate the transfer function. Again, we will use apply this same formula, Mason's gain formula, to calculate the overall transfer function and gain of the signal flow graph. Now the formula, again, the transfer function formula is again P1 delta 1 plus P2 delta 2 up to Pk delta k divided by delta. So again, we need to calculate these values P1, P2, P3, and delta 1, delta 2, delta 3, and delta. Now, how many forward paths we have in this signal flow graph? If you will look closely, then we have 3 forward paths in this problem. This one, which goes straight from node 1 to node 5, is path 1, and the second one is like this, goes through E, and then this one, the second path, and the third one is going through node 2, node 4, and node 5. So there are basically 3 forward paths. Let me represent the path gain at the forward path P1, which goes like this. And let me draw this here. 2, 3, 4, and 5. Node 1, node 2, node 3, node 4, node 5. The gain between node 1 and 2 is A. Between 2 and 3 is D. Between 3 and 4 is F. And between 4 and 5 is I. So the path gain of P1 forward path 1 is A, D, F into I. The second forward path, which goes like this, from node 1, node 2, and then node 2 to node 3, and node 3 to node 4, node 4 to node 5. So this gain is A, 2 to 3 it is E, and from 3 to 4 it is F, and 4 to 5 it is I. The path gain at the second forward path is A, E, F, I. Similarly, we have forward path 3, which goes like this, from input node 1, node 2, node 3, let me again redraw this. So that is, we have already made this forward path. So we have node 2 to node 4 directly. We will go node 4 and then node 5. So this gain is H, this 4 to 5 is gain I. So in this node 1 to node 2 we have gain A. So overall gain, path gain for this forward path is A, H, I. So we have only 3 forward paths in this problem. So P1, P2, P3. Now, in order to calculate delta, we first need to calculate the individual loops. So how many individual loops we have in this? So if you can look closely, we have 5 individual loops. Let me define those loops with L1, L2, L3, and L4, L5. First of all, what is loop 1? So you can clearly see. Let me highlight this also. So this loop just starts and terminates at the same point. The loop gain, overall loop gain equals to B. So this is our, let me, again, this is our loop 1. So this value is equals to L1 equals to B. And similarly, L2, which starts and terminates. So the starting node is 2, goes to 3, and again terminates at 2. The loop gain D into C. D into C. It is second loop, the loop 3, which starts from node terminal 3 and terminates again at 3, is having loop gain equals to F into G. Similarly, loop number 4, which starts from node number 2 and goes like this from G to C. So the loop gain for this is D, F, G into C, and loop number 5 is your starts from 2, goes through E and C. So it is T into C. So these are the 5 loops we have in this problem. Let me also draw these loops so that you can clearly understand. This loop L1 is started from node number 2 and terminates at 2. So it goes like this with the loop gain B. The second loop L2, which is D into C, starts from node number 2 and goes to node number 3 and terminates again at 2. So this gain is D, this gain is C. So this is loop number 2. The loop number 3, which is F into G, it starts, let me go here. Node number 3 starts, goes to node number 4 and again terminates at 3. So the gain is overall loop gain is f into g. The fourth loop, this L4 starts from node number 2, goes to 3, goes to 4, goes to 3 again, and again goes to 2. So this is how it goes. This is node number 2, 3, and 4. The gain here is D, F, this is G, and this is C. The last loop, loop number 5, it starts from node number 2 and it goes to loop node number 3 like this. This gain is E and goes like this, C. So these are the 5 individual loops we have in this problem. If we talk about the non-touching loops, so you can clearly see that node number 2 is present in all these loops except this loop. So this loop and this loop, loop number 1, L1 and L3 are the non-touching loops. L1 and L3 are the non-touching loops. Otherwise, all the loops are touching. There is a common node, node number 2 in all the loops. Node number 2 is common in all the loops except this node number loop number 3. So these loop number 1 and 3 are the non-touching loops, and so we can write here the non-touching loop NT1. NT1 is equal to L1, the product of individual loops which are non-touching, L1 and L3. So if we multiply these two, B, F into G, it is the non-touching loop. Except this, there are no non-touching loops. So next we will calculate the value of delta, which is 1 minus sum of all the individual loop. So this will be L1 plus L2 plus L3 plus L4 plus L5 plus sum of all the gain product of non-touching loops. So there is only one non-touching loop, so it will be NT1 only, minus product of 3 non-touching loops. There is no such case in this question, so this will be 0. The value of delta 1 is the value of all the values of delta after removing all the loop gains touching the forward path P1. So this is the forward path P1, and all the loops are touching this forward path P1. So the value of delta 1 comes out to be 1 minus, since all these are loops and non-touching loops are touching forward path P1. So this value comes out to be 0. So delta 1 is equals to 1. Similarly, delta 2 will also be 1 and delta 3 will also be 1, because all these paths P1, P2 and P3 are touching all the loops present in this question. So finally, we can determine the transfer function, which is E1 delta 1 plus E2 delta 2 plus E3 delta 3 divided by delta. Now E1, P2, P3 we have already determined. Delta 1, delta 2, delta 3 all equals to 1, and delta we already determined. We can put these values in this final expression to get the transfer function value. I hope you understood this problem. Thank you.